Okay, today we're going to learn measures of linear relationship. Measures of linear relationship is to answer the question, how do we determine the linear relationship of two variables? We're going to talk about four concepts. They are covariance, coefficient of correlation, least square line, and coefficient of determination. So in this class, today, we're going to look at the first two concepts. Okay, first, let's have a look at covariance. Okay, again, covariance is very similar to variance. The difference is that variance is to measure the dispersion of one variable, and covariance is to measure the relationship between two variables. So similar to variance, the formulas for population and sample are different. So first, let's have a look at the formula of covariance for population. Okay, the population covariance is denoted as sigma xy, and sigma xy equals 1 over n times the sum of the two parts here. First part is xi subtracted by mu x. Second part is yi subtracted by mu y. Xi is each individual in the population. Yi is the second variable. Second variables, each individual in the population. Mu x is the mean of x. Mu y is the mean of y. This is the definition of covariance. Also, we can use the derived formula here. Mu xy equals 1 over n times, okay, first part is the sum of the product of xi and yi. I ranges from 1 to n, minus 1 over big N xi, sum of xi times the sum of yi. Again, I ranges from 1 to n. Okay, you can choose either formula to calculate the population covariance. Okay, please write these two formulas down in your notebook because we're going to use them to do an example. Okay, I'll give you 2 minutes. Okay, have you finished? All right, next, let's have a look at how do we calculate the sample variance. Okay, sample variance is very similar to the population covariance. The only difference here is first, we use SXY to denote the sample variance. Sample covariance. Sample covariance SXY equals 1 over n minus 1. Remember, pay attention here. The divisor is n minus 1, not n. Okay, and times the sum of two differences. First one is xi minus x bar. Second part is yi minus y bar. Xi is the individual in the sample for variable x. Yi is the individual in the sample for variable y. And x bar means the mean of x. Y bar means the mean of y. Okay. Also, please write this down in your notebook as we're going to use it for some examples. Okay, again, like the population, we can use the derived formula for sample like this to calculate sample covariance. Okay, I'm not going to show you the proof of this. If you're interested, you can do this after this class. Okay, please write this down in your notebook. We're going to use it in our next example. Okay, have you finished? Okay. Next, let's have a look at some example. Okay. Consider the following three sets of data. Okay, for example, set one is x is 2, 6, 7, and corresponding y values are 13, 20, and 27. Calculate the variance of x and y for each sample set. Okay, there are three sets of data, and it asks you to calculate the covariance of x and y for each set. All right, here I will show you how to calculate covariance for the first set and leave the other two sets for yourself. Okay. All right. Remember to calculate the covariance. First of all, we need to make clear if this is a sample data or population data. So here it already says each sample data. So this means these are sample. So we'll use a sample covariance. Okay, sample covariance, let's recall the formula, which is SXY. Okay, SXY equals 1 over n minus 1 times two parts, right? First part is the sum of the product of x and y minus 1 over small n times the sum of x times the sum of y, right? Okay, so here we need to find the sum of the product of x and y, and sum of x and sum of y. So let's list the table here. Okay, we have x and y. Okay, because we need the sum of x, y, so we need to add a column called x times y. Also, we need anything else? No, we only need x times y, right? So let's calculate the product of x, y for each row. First row, this is 26. Next row, we have 120. Okay, next. We have 189. And then we need to calculate the sum of each column. First column, the sum of x is 15. Next column, the sum of y is 60. Okay, next one, the sum of the product of x and y is 335. And now we have all the numbers we want, right? And then we can plug back into the formula. 1 over n minus 1. N is 3, right? N is the number of pairs. So 3 minus 1 times product of x times y is 335 minus 1 over 2. Sorry, 3. Sum of x is 15. Sum of y is 60. And in this way, we can calculate sample covariance. This is 1/2 times 35, which is 17.5. So this is our sample covariance. Okay. Any questions? No? All right, I'll leave the other sets for yourself. Please calculate the covariance for the second set and the third set. Okay? I'll give you 5 minutes for this. All right, have we finished? What's the result for the second and third data? So when you have this pattern, you will get a very large negative number like this. Okay, the third one, if we plot this, you can see that first it will have a 220. Okay, suppose 220 here. Next one, you get a 627. 627 is about here. Next, we get 713. 713 is here. Okay, as you can see here, there is no particular pattern, right? As x increases, y could increase or decrease. There is no apparent pattern. So in this case, normally you will get a small number around 0. Okay, so this is how we can calculate the covariance using manual method. So again, like variance, we can also calculate the covariance using a spreadsheet. Okay, next I'll illustrate how we can do this in the computer. Okay, we have two variables, right? For x, the values are 2, 6, 7. And for y, the corresponding y values is 13, 20, and 27. This is the same data as we used in our previous example, right? Okay, first, to calculate sample covariance, the formula we're going to use is called COVR, COV. When you put equality sign followed by COV, you can see there are three formulas, right? Because they are sample data, we should use the third formula, covariance for sample. Okay, click this. There are two parameters in this formula. First one is your x or y. You can just drag down, select A2 to A4. Okay, and separate this with a comma sign. And the second parameter is all y's. Again, drag down to select B2 to B4 and red brackets and hit enter. Then we'll get the covariance between x and y automatically. This is 13.5, which is the same as the one we have calculated here, right? Okay, next, let's have a look of the second data set, which is 2, 6, 7 for x, and corresponding y values 27, 20, and 13. Okay, this time, again, hit the equality sign first, and COV. First parameter are x's, second parameter are your y's. Or we have used the wrong formulas. So we COV and select the last, which is covariance.s. As you can see here, covariance between x and y for the second set is minus 17.5. Okay, the third set, 2, 3, 7, and corresponding y values are 20, 27, and 13. Okay, again, we use equality sign followed by COV and choose the third formula there. sorry, covariance dot s. First parameter are x's, second parameter are all y's. Okay, again, as you can see here, the calculated covariance is minus 3.5. So this is the same as the value we have calculated here, right? So this is how we can use the computer to help us to calculate covariance. All right, so I'll give you 5 minutes to have a play of this. If you don't have access to Google Sheets, please use WSP or Excel in your local machine, okay? All right, have you finished? Okay, we can take 10 minutes break, and after that, we'll introduce the second concept, which is called coefficient of correlation. Okay, please return in 10 minutes. Okay, welcome back. And now let's have a look at what is coefficient of correlation. Okay, here we take an example of two variables here, x and y. Okay, the coefficient of correlation is defined as a ratio between covariance and standard deviation of x and y. Okay, again, for population coefficient of correlation, we use a letter rho to denote it. Rho equals sigma xy divided by sigma x and sigma y. For sample, the sample coefficient of correlation is defined using a letter r. R equals sxy over sx and sy. Okay, please write them down in your notebook. And next, we'll see an example to illustrate how we can calculate this. Okay, have we finished? Okay, before we proceed to the example, let's introduce the interpretation of coefficient of correlation. The reason why we need to introduce this measurement. Okay, so this coefficient answers the question, how strong is association between x and y? The advantage of this coefficient of correlation over covariance is that it has a fixed range from -1 to +1. Thus, if the two variables are very strongly positively related, the coefficient value is close to +1, which means strong positive linear relationship. If the two variables are very strongly negatively related, the coefficient value is close to -1, which means strong negative linear relationship. Okay, if you have no straight line relationship, that is indicated by a coefficient close to 0. Okay, in other words, when you have a relationship that is shown in the top right corner, usually you will get a value very close to +1. That means strong positive linear relationship. That means as x increases, the other variable y also increases. On the contrary, if x increases and y decreases, you will get coefficient of correlation very close to -1. That means strong negative linear relationship. When you get a positive or negative number around 0, that means no or very weak linear relationship, which can be shown in the graph in the middle, in which there is no apparent patterns. That means as x increases, the other variable could increase or decrease. You can't see any apparent pattern there. Okay? All right, now let's have a look at how do we calculate the coefficient of correlation using the previous example. Okay, in previous example we have 3 data sets and we have calculated their covariances as follows. Okay, the question now becomes, how do we calculate the coefficient of correlation of the two samples for each set? Okay, I'll show you the solution for the first set, and I'll leave the other two for yourself. Okay, all right. First, let's list the sample covariance. How do we calculate this? Let's write the formulas here. Sample It's better to write it here. Okay, sample, because they are sample data, right? Sample coefficient of covariance. Sorry, sample coefficient of correlation. Is calculated using this formula. That's R equals SXY over SX over SY, right? Okay, suppose here we do not know SXY yet. We'll start from the very beginning, okay? So first of all, we need to calculate SXY. SXY is a covariance between X and Y, right? And it is calculated with this formula. Right? So first of all, we need to add a column X times Y, because we're gonna use this value here, right? Okay, so SXY is 26 for the first row, 120 for the second row, and 189 for the third row. Next, we need to calculate the sum of each column. Sum of x's is 15, and sum of y's is 60, and sum of the product of x and y is 335. Okay, and this gives you the value of SXY, which is 1 over 3 minus 1 times 335 minus 1 over 3 times 15 times 60, right? You have all the numbers here, and the result here is 17.5, which we have already got in our previous example. Okay, next, we have already know that SXY is 70.5. Next, we need to calculate SX. SX is the standard deviation of X, right? So in order to calculate the standard deviation of X, we need to find SX squared, which is the variance of X, right? Remember that the formula used to calculate the variance is 1 over n minus 1 times sum of all x squared minus 1 over n sum of all x's as a whole to the second order, right? So here we need the sum of x squared. So we need to put another column called x squared. So for the first row, x squared is 4. When x is 6, x squared is 36. When x is 7, x squared is 49, right? And sum of x squared is 89. So let's put all values in this formula. 1 over 3 minus 1 times sum of all x squared is 89, right? Minus 1 over 3 times the sum of x's is 15, and 15 raised to the second order. Okay, in this way, you will get the variance of x, which is 7. So Sx is simply the square root of variance, which is square root of 7, right? Okay, using the same method, we need to calculate variance of y. Okay, again, formula look the same. Sum of all y's here to the second order, which is 1 over 3 minus 1. Next, we need all the y squared, right? So let's put another column called y squared. When y is 13, y squared is 169. When y is 20, y squared is 400. When x is 27, y squared is 729. And then let's calculate the sum of all y squared, which is 1298, right? Okay, so put the values here, 1298 minus 1 over 3 times the sum of all y's, which is 60 to the second order. So the final result of the variance of y is 49. Okay, so sy is square root of 49, which is 7, right? Now we have sxy, sx, and sy. Then we can put all these values here. Let's use another color. Okay, this equals 17.5 square root of 7 times 7, right? And then now we have the coefficient of correlation, which is approximately 0.945. Okay? And you can see here 0.945 is a positive number that is very close to 1, right? So the conclusion is x and y have a very strong positive linear relationship. Okay, pay attention to the wording here. Very strong positive linear relationship. All right, understand? Any questions here? Okay, if you don't have any questions, I'll leave the rest of the data sets for you to calculate their coefficient of correlation, okay? Please first copy the other two sets onto your notebook. And using similar method to calculate their coefficient of correlations. Okay, all right, have you finished? Okay, I'll show you answers here, okay? So the first for the first data set, the coefficients of correlation is 0.943. The second set is negative 0.943. For the third set, the coefficients of correlation is minus 0.189. As you can see here, for the third set, this value is very close to 0. That means there is a weak or no linear relationship for the third set of data. Okay, note that these values are approximate values, because when you calculate the square root, usually we'll use approximation, right? So this is a little difference the values here. It's probably because of the rounding up or rounding down. Okay, again, we can use tools to help us find coefficient of correlation. Okay, let me show you how to do this. Coefficient of correlation, we can use the formula CORR. Okay, and click CORREL and choose your first data set separated by a comma sign and choose the other data set. So as you can see here, the Google Sheets can automatically calculate the coefficient of correlation for us, which is 0.945 for the first data set. Okay, for the second data set, again, use CORREL formula. First variable, second variable, and you will get a minus 0.45 correlation of a coefficient of correlation. Okay, for the third data set, again CORREL, first data set followed by the next data set, and the coefficient of correlation is minus 0.189. Okay, so if you are using a tool, the task is very easy. So now you should be able to calculate the covariance and coefficient of correlation using both manual method or with the help of a computer tool. Okay, have a look at this.